Alright, welcome guys. This is the video on Snell's law. If you haven't already watched the index of refraction video or the intro to refraction video, please go watch those two first. You're going to need to know those pieces of information before you attempt to understand this video. What we're going to do is define and use Snell's law to determine the details of refraction. Now, first I want to start off by reminding you of what we call each little aspect in the refraction diagram. So what's happening is this is the incident ray, this is the refracted ray, and the angles they make with the normal line we call the angle of incidence and the refracted angle. Okay, if you don't know those, this is the first time you're hearing those, you want to go back and watch that intro to refraction video. What I'm going to show you is this PhET simulation that you've seen before. We're using a blue light this time instead of red. We're feeling a little blue today. So what we want to see is that if I change the angle of incidence, which is this angle here, what also changes is the angle of refraction, which is this angle here. So if I play around with this angle, that angle changes, and vice versa. Now that's why I've written theta I and theta R as the first two things that the refraction depends on. It depends on the incident angle, which changes the refractive angle, and because these two things get changed when you play around with either of them, that means the refraction depends on those two. Now another thing I can show you is if I change the index of refraction. So this is the index of refraction for medium 2, or sorry, for medium 1, and when I change it, the refraction is changing. If I change the index of refraction for the medium 2, the refraction also changes. This means that the index of refractions also determine the refraction. So that's why this N1 is written here and this N2 is written here. And basically all of your sciences, and especially physics, when you determine what variables something depends on, that gets you a lot closer to determining what the equation will be. So if you just look at theta I and theta R, N1 and N2, if I click this and drag to the left, you'll see that this equation includes only those variables. So let's talk about that. Snell's law is that N1, which is the index of refraction for the first medium, multiplied by sine of theta 1, which is the incident angle, will always be equal to N2, which is the index of refraction for the second medium, multiplied by the sine of theta 2, which is the refracted angle. Okay, and this is very, very, very important, very significant, because with Snell's law we can predict how a beam of light will refract, and it can also be used to determine an unknown medium. So knowing this piece of information helps us find a missing piece of information, which just turns out to be what every physics equation does ever. Now I'm going to solve two examples for you. If you want to pause right here and attempt these on your own, please do, and then you could fast forward a little bit to see if your answers match mine. But let's start solving now. So example 1 states, for a ray of light that travels through air and strikes flint glass with an incident angle of 35 degrees, find the angle of the refracted ray. So what I'm going to do first is just highlight the pieces of information that the question gives us. The first piece of information is that it flies through air. The ray of light is traveling through air and it strikes flint glass. With an incident angle of 35 degrees, find the angle of the refracted ray. So I'm just going to write a small little given list here. And first piece of information that's given is that the light goes from air and travels to flint glass. Now knowing the materials is important because that gives us the indices of refraction. We'll get to that in a bit. We also know that the incident angle is 35 degrees and the variable we need to find is theta r, the refracted angle. Now how we're going to start by doing this is looking at our given pieces of information. We need to choose a relationship that relates all of our pieces of information with what we need to find. And obviously it's no coincidence that Snell's law fits perfectly. So I'm just going to write Snell's law right here. Ni of sine theta I equals Nr times sine theta r. Now what we're going to do is fill in all the pieces of information and then solve for theta r. From here on out it's just algebra, but I'll walk you through it. So because Ni is air, air has a refractive index of 1.000293, and we're just going to complete the rest of it. Sine theta I is 35 degrees. Now flint glass is the second medium, and that has a refractive index of 1.66 sine theta r. Now we're going to just do this multiplication. I'm just going to do it on my calculator. 1.000293 times sine 35. Make sure your calculator is in degrees mode and not radians mode. That gives us a value of 0.574 equals 1.66 sine theta r. Now the next step is to divide the 1.66 over. So this comes over like this. This is a multiplication here. This will be a little division here. 0.574 divided by 1.66 gives us a value of close to 0.346 equals sine theta r. A lot of students mess up here because they think they've reached the end. What we're searching for is theta r and not sine theta r. So don't forget to do this last step. This last step is to take the sine inverse of 0.346. The sine inverse of 0.346 is equal to 20.24. 20.24 degrees is our theta r. Okay, let's change this to red. Let's just circle. There you go. Cool. Let's try example 2 now. Now example 2 says find the incident angle for a ray of light traveling through water, cool, that's medium 1, and reaches flint glass. Let's change this back to black. And refracts with an angle of 25 degrees. Now every word in this question is important because it tells you pieces of information. This says it refracts with an angle of 25. In our first example, it said that it was incident with an angle of 35. So in this case, our given values are water to flint glass. We also know that it refracts with an angle of 25. And what we need to find is the incident angle, theta I. Now I'm just going to start by writing Snell's law. And filling in the pieces of information. Water has an index of refraction of 1.33. Now all these numbers that I have just kind of memorized in my head are 1.33. Are from, you can find them through tables or figures. These values are normally just given to you. I just kind of have them memorized. I'm kind of a nerd. Sine theta I. Theta I is 25. Now it reaches flint glass. Flint glass had a refractive index of 1.66. Oh, see, I've already made a mistake. I've put the angle in the wrong place. Theta I is what we need to find. So undo, 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 undo. Theta I is an unknown piece of information. 1.66 goes here, and sine 25 is here. Now what I'm going to do is do this multiplication real quick. 1.66 times sine 25 gives you a value close to 0.702. And 1.33 is over here. Sine theta I. The next thing is to divide this guy over. So we get sine theta I equals 0.702 divided by 1.33. That gives you a value of 0.528. Now don't forget this last step. We have to do the sine inverse. So sine inverse theta I equals sine inverse of 0.528. That gives you a value of 0.528. Nope, that's not right. 0.528. 31.8 degrees is theta I. Change it to red. Highlight the answer. And there we go. So, to check for your learning, pause here and try to answer these questions. First one is, what are the variables that affect refraction? And the second one is, try to do this without looking back or looking at your notes. Just try to write down what is Snell's law. See if you can remember it off the top of your head. Now, to summarize this video, the index of refraction for the first and second medium, the incident angle, and the refracted angle are all related with Snell's law. Snell's law is index refraction 1 sine incident angle, which equals to index of refraction of medium 2 times sine refracted angle. Thanks for watching. If you have any questions, make sure to throw them in the comments.